This is the last of the 4 videos about kinetics. We're going to cover integrated rate laws and half-time. So we have learned about differential rate laws, or generically speaking, rate laws. Those are differential equations, so basically they describe the change in concentration over a certain amount of time. Using calculus, we can integrate the rate law and obtain an integrated rate equation, and this allows us to do the math in terms of how much reactants is used up or how much products is made in a certain amount of time. So integrated rate laws are the mathematical relationship that we use when we want to calculate how much of the reactant is left. We can use a graph or we can use an equation. In the graphing option, what we are putting on the y-axis is different depending on the order of the reaction. We kind of saw that in the very first video. If we have a zero order reaction, we plot the concentration and the graph is already linear. If we have a first order reaction, the graph is going to be a curve, so we need to plot the logarithm of the concentration. If the reaction is second order, we get a steeper curve, and we need to plot, in order to make it linear, we need to plot the reciprocal of the concentration. So these are the 3 graphs, right? So you notice that if you go in order from 0 to first to second order, what you're plotting on the y-axis happens to be in alphabetical order, so this could be a way to remember. This can very much be a question in an exam. Giving you the graph, tell me what order it is, you need to look at what is on the y-axis. So in the bottom part, you see that those relationships reflect a linear graph. So if y for 0 order, you're plotting the concentration directly, and the slope is going to be minus k, and the intercept is going to be a0, the initial concentration. So this would be the initial concentration, and the slope of this line is going to give you k. In the first order, you're plotting the logarithm of a. Again, minus k is the slope, and the intercept is the logarithm of the initial concentration. For second order, you're going to plot the reciprocal. The slope this time is positive, so it's already k, and the intercept is the reciprocal of the initial concentration. Now, most of the time, if not any time, you are going to be given problems in terms of integrated law that refers to first order, because the math is simpler and because they reflect, first order is the order of radioactive decay. So for example, in this case, you have a first order kinetics, and they are asking you to calculate how much it takes for 95% of the original amount to disappear, given the rate constant. So you're going to look into your rate laws and pick the first order. Now, in the even in the final, the ACS final, that at this point we're not going to use, but they are given, so you don't have to memorize it. No? They may be given explicitly, like say in 0 order is so and so, first order is this, and then second order is that. Or maybe sometimes you may not have the indication which one is 0, which one is first, and which one is second, but they're given in order, so it's relatively easy to identify them. So the trick here is to figure out that if 95% is disappearing, it means that you have 5% left. So the amount that you have left is the amount you have at the time t. So it means that A here is going to be 5%. That would be 0.05. K is given. T is the time that is going to take, right? That would be your unknown. And the initial amount is 1. So it almost looks like they're not telling you how much you have at the beginning and how much you have left. But it's 95%. If it's first order, this is why first order are always picked. It's always going to take the same amount of time to for the same percentage to disappear. So if you start from 1,000 molecule, it's going to take a certain amount of time to be left with 50. But if you start from 100 molecules, it's going to take exactly the same amount of time to be left at 5, right? So this means that you can take any arbitrary amount. So you can take, for example, 100 and 5, or you can take 005 and 1. That would work equally well. So for example, if you take A0, that would be the initial amount equal to 100, this will make at the time t the amount left 5. So you can rearrange by bringing this term on this side of the equality, and the difference between two logarithms is equal to the logarithm of the ratio. So you kind of need to remember your logarithm here. And if you have been you're probably in some level of calc, so this may be relatively old stuff for you. So you get the logarithm of 5 divided 100. That's exactly the same number you would have gotten if it was, you know, 1 and 005, or if it was 2 and 010, or if it was 500 and 025 and 25. So it doesn't matter what, because the ratio is always going to be the same. It's going to be 005. And then you just want to keep 3 sig fig. The sig fig here is kind of hard to determine because actually it would be 2. So yeah, so 2 sig fig. So we have kind of already introduced the concept of half-life, because I told you that for first order, the amount of time that it takes to reduce the initial amount of substance over a certain percentage is always going to be the same. Now there is a particularly useful percentage that is 50%. So the amount of time that it takes for the initial amount to be cut in half is going to be called, guess what, half-life, right? So in a first order reaction, that amount is constant. So if I want to go from a 0 to half of a 0, it's going to take me, let's say that these are, I don't know, hour. So if I want to go from a 0 to half of a 0, it's going to take me an hour. If I want to go from 1/2 of a 0, cut it in half again, so 1/4, is going to take me another hour. So let's say that, for example, this was 1000. This would be 500. This would be 250. And this would be 125. Okay, so I start with 1000 grams. It takes me an hour to go down to 500 grams. Then it takes another hour to go down to 250 grams. And then finally it's going to take me another hour to go down to 125 grams. So the half-life is constant. This is true only for first order. So this is why first order problems are favored. Also because, as it happens, this is the behavior of radioactive isotopes that are decaying. So there is a practical interest. So, you know, all those isotopes that are used in medical application, for example. As I said, the fact that the half-life is a constant works only for first order. If you have 0 order, the half-life gets smaller and smaller. The first half-life is this one, and then to reduce again into half, it takes a much shorter time, and then for this it takes an even shorter time. For first order, as we said, is a constant. For second order, instead, the half-life goes up. So the second half-life is longer, the third half-life is longer. They kind of make sense, because if it's second order, it means that you need collision between two molecules. So the lower is the concentration, the harder it is for the two molecules to find into each other and collide. Therefore, it's going to take more time for a certain amount of them to disappear. So sometimes questions about half-lives tend to be qualitative and not quantitative, meaning it's not so much that you have to do math, is that you have to do some reasoning about it. So you have a set of data, and they may ask you which order is not. Because what you have to be careful with is considering what you have on the y-axis, because that's what's different depending on the order. So the fact that you have the concentration, so there is no manipulation whatsoever. This is sort of the rough data. If it would have been zero order, you would have had a straight line. If it would have been second or first order, it would have been a curve. Now, that as a straight line doesn't really, but it's hard to draw with the mouse. But for second order, it would be more like a shape like that. So this to me looks first order. However, just by eye, telling the difference between the two curves is hard, but for sure is not first order. So which order is not first? I'm sorry, zero, because it's not linear. What is the half-life of the element? So to go from 1 to 0.5 is taking 3 minutes, and then to go from 0.5 to 0.25 is going to take another 3 minutes. So the time is the same. That's telling me it's first order, because that's the one for which the half-life is constant, and the half-life is 3 minutes. What is Q after the second half-life is going to be 0.25%, so 0.25. At what time has 87.5 of the original sample decayed? Now you may think you need an actual formula to do that, because 87.5 doesn't look like any particular number. But think about that. If you start from 100%, first half time you go down to 50%, and you have 50% left. After a second half-life, you have 0.25%. That means you have consumed 0.75. After another half-time, you have 0.125 left. That means you have consumed 87.5%. So it's going to give us a total of 3. So this table summarizes all the different information about each order of reaction. So for the rate law, you don't have to worry too much, because that's basically the definition. So if it's zero order, the rate is constant, it is independent. If it's first order, it's proportional to, it's linearly related to the concentration. If it's second order, there is an exponent to 2. So the integrated rate law are given, right? So these are given in the test, even in the final. The units of K, those are not given, but they are easy to figure out from the rate law, because rate, the definition of rate is that it's the molarity, the change in molarity, so it's a molarity divided time. So if you put that in place of rate and you simplify for the concentration and you solve for K, you get the unit of K. Why are units relevant? Sometimes there will be problems that are a little bit trickier, where they do not tell you apparently what order the reaction is, but they do give you the value of K with the units. So because the units are different, just looking at the units, embedded in that information is the order. So if you have a problem and I'm not telling you that's first order, the reaction is first order, but K, I'm telling you the K is 3 seconds to the -1, automatically you know that that reaction is first order because those units work only for a first order reaction. I'm not going to do that in the test, right? So what you need to remember is what makes a plot linear. What kind of manipulation makes a plot linear? You have to do nothing for zero order. For first order, you have to use a logarithm. If the point is to get it linear, it doesn't matter if you use a natural logarithm or a decimal logarithm. You still get a straight line. Obviously, the numbers are going to be different. If you have second order, you want to plot the reciprocal of the concentration. Remember that the slope is negative for the first two and positive for the second one, because they may give you the graph and tell you to figure out the order by looking at the graph. And finally, the half-life. I will give the half-life in this test. In the final, it's probably not going to be there. It's no big deal for two reasons. Number one, half-life is typically a problem for which you get first order. So it's really only one that you need to remember. And you are given the integrated rate law for first order, so all you have to do is set A at time t 50, A0 100, and solve for that, and you get the half-life. So it's easily obtained by the integrated rate law. So as I said, half-life are typical problem with half-life are typically given for first order reaction for sake of simplicity of algebra. And as you can see, you can calculate the half-life out of the integrated rate law by setting AT twice as big as A0. So it becomes the logarithm of 0.5. So that's the formula for the half-life. Most of the time there are shortcuts for which you don't even have to use it. So let's see a couple of examples. Ammonia decomposes into its element, that would be nitrogen and hydrogen. According to a first order kinetics, you're given the K units second to the -1 are consistent with the first order. So they could have almost, you know, a teacher could have almost drop this part, decomposes into the elements, and the K is this. And you should have been able still to tell it was a first order kinetic. Why don't you need the order? Because you need to pick the right formula. So as I told you, it's extremely unlikely you get a problem like this for second order or zero order. 99% of the time is going to be first order. So you go and pick the formula for the first order half time. And because you know K, right? So you plug K, and that's the end of it, basically. So let's see another example. This shows you a shortcut, and that's a shortcut that typically you can apply very often, especially in situation like a final exam, where they tend to give you less math-heavy problems. So supposedly more simple. Again, it's simple when you know how to do it, right? So you have the half-life of zinc, 2.4 minutes. You start from 100 grams. How much would you have left at 7.2 minutes? So there is no mention to the order. That's because they assume that you know that if it's an isotope that's decaying, it's first order, period. So the question is, if instead of using a formula, can I guess? And I can guess, especially if the time is a whole multiple, it's a simple multiple of the half-life, right? So if I divide 7.2 by 2.4, I get 3. So 7.2 is exactly 3 half-life. So you take your hand and you start counting. 100, thumb up, divided by 2, the first decay, you go down to 50 grams. Second decay, index finger, you go down to 25 grams. Third decay, middle finger, you go down to 12.5 grams. So 3 steps, 12.50 remaining. If they're asking you how much was decomposed, then it would be 100 minus 12.50. Let's see another example. A substance undergoes first-order decomposition. After 40 minutes, at 500 Celsius, you have only 12.5% left. So what's going to be the half-life? So you have the temperature. You don't really have to do anything with the temperature. I mean, the temperature does affect the speed of a reaction, so it's kind of proper to provide it, but it's not like you have to do any math with it. The important numbers are that you have 40 minutes to go from 100% to 12.5%. So you could think that you need to use the formula, but to use the formula you need K, and you do not have K. So let's see if we can use a similar approach to the one used in the other slide, right? So how many half time does it take to go from 100% to 12.5%? So let's go backwards, and if we figured it out that it takes 3 steps. So those 3 half-lives correspond to 40 minutes. So really all you have to do is divide 40 minutes times 3, and you get 1 half-life that is 13.3. So let's see the last example. We have a radioactive isotope that as any other radioactive isotope is going to follow first-order kinetics. The half-life is 14.3 days. How long does it take for 95% of the sample to decay? So we need to use the integrated rate law, because whenever it's asking you how much time does it take, that's integrated law. And that's the law. And the law requires, so the K, right? So we know that A is going to be, so at the time T, we have 5% left, because 95% is gone. And A0 would be 100%. So T is our X, but we don't have K, so that's kind of a problem. However, we are given the half-life, and for first order, we can remember the half-life is given by this expression. So actually, knowing the half-life, wrong thing, going the half-life allows us to calculate K. So we can calculate K this way, by dividing 0.693. So we bring K on this side, so we divide by the half-life here, so that gives us the value of K. And now we can just, to quote you guys, plug and chug, and substituting into the integrated rate law. So that's pretty much all we have to learn about kinetics. Have a nice Easter, and get your skis out, because I don't know where you are, but here it's all white right now. See you guys.